In this video, I'm going to extend our variable or our single variable results to multivariable. So let's say that instead of having a seesaw, I now kind of have a whole spread out seesaw. And I'm going to put it on two different fulcrums. One fulcrum is going to run along the x-axis, and one is going to run along the y-axis. And let's say I wanted to calculate moments of these different points with different weights on them. Well, if you remember what we did in the single variable case, we essentially took the signed distance, because we had x coordinates that could be negative, and I multiplied that by the mass to get the moment. So we see that the moment in respect to the x-axis is, well, the signed distance now is going to be given by a y-coordinate, and I'm multiplying by the mass. And then, if we go to the continuous case, I get that the total moment, kind of using the same logic as before, is going to be given by a double integral over a region of y times the density of my point, and that would be the total moment. Similarly, and this is again in respect to the x-axis, and how could I use this? Well, I could take the total moment divided by the mass to find a better place to put my fulcrum so that this thing is balanced. So looking at my example here, I have a couple weights above, one below. Maybe it looks like my new fulcrum should be like here or something. I don't know. That doesn't look terribly right, but maybe. We'll go with it. And we could do the same exact thing here. We'd get that the total moment in respect to the y-axis is going to be given by this. Now it's going to be x times the density. And then if I wanted to find where to put my new fulcrum, I would again divide the total moment in respect to the y-axis by the mass, and maybe I'd get something like this. So what you'll notice is that this tells me an x coordinate, and this tells me a y coordinate. I'm going to call these x with a bar and y with a bar. And essentially, if I wanted to then find the balancing point of the whole system, I would just find where these things cross. And where those cross is going to be the center of mass, which is going to be my x coordinate and my y coordinate. So that would be the point where I'd need to be in order to balance this whole system. So with that in mind, let's just do a quick example. And there's a good thing we want to talk about. So center of mass is a problem we'll be finding when density is uniform. So like again, we're talking about the continuous case here, where we don't actually just have a whole bunch of weights, we actually have like a density varying along this region. When that density is uniform, we get this center of mass is called the centroid. So let's do an example. We're going to we'll find the centroid. Let's do something that should be horribly unsurprising just so we can do some quick math. Of the triangle, maybe not as horribly unsurprising as I was hoping, as the triangle with vertices 0, 0, 0, 1, and 1, 0. So I'm going to set up a double integral of x dA to get my x coordinate. My density just needs to be uniform, so we'll just have it be 0. Or sorry, have it be 1, so I don't need to write it. Over the integral of just dA. This is just the area. This is going to equal, well, this is a double integral over the region looking like that. So I see that this is going to be, for example, I have the line y equals 1 minus x on top and 0 on the bottom. So this is the line y equals 1 minus x, so I'll have dy, and then we'll have dx on the outside. And then this will be over the area of the triangle. It has base height 1, and then, so that's just going to be 1/2. Let's take a closer look at our integral. That's going to be the integral from 0 to 1 of xy, evaluated from 0 to 1 minus x dx over 1/2, which will equal the integral from 0 to 1 of x minus x squared dx over 1/2. We'll just write that as 2. So that's going to be 2 times x squared over 2 minus x cubed over 3, evaluated from 0 to 1, which will be 2 times 1/2 minus 1/3, which will be 2 times 1/6, which will equal 1/3. Okay. To set up my y coordinate, I'm going to go ahead and observe that this line is also given by x equals 1 minus y. So we'll have the integral now of y over the area. And I'm going to make the rather cheeky choice to write this as this. Which I think we can convince ourselves is exactly the same as the integral we just did. So that's going to also give us a value of 1/3. So the centroid would equal 1/3, comma 1/3. And there you go. So we found the centroid of this region by doing a couple integrals. And yeah, so that was that problem. Oh, but I wasn't quite done. There's one last thing we need to talk about, and what about 3 dimensions? I will spare you the pictures. I will let your intuition guide you. If we're trying to find the total moment, basically we're now going to be having our fulcrum be essentially plane. So like the total moment in respect to the xy plane, or we'll start with the yz plane for reasons which should make sense once I write stuff out. That's going to be the triple integral of our region times x delta xyz dv. If we do the xz plane, That's going to be the triple integral of y delta xyz dv. And if we do the yz plane, or the xy plane, that'll be the triple integral of z delta xyz dv, just like what we did in the previous case. Then if you want to find your center of mass, or centroid, you're going to let your x-coordinate be the triple integral of x, xyz dv over the volume. You're going to let y be the triple integral of y, xyz dv over the volume. And you'll let z be the triple integral of z delta xyz dv over the volume. And then you use a similar process to what we just did. So there you go. Not horribly unsurprising, but it just, is an extension of what we did in the two-dimensional case.